Okay, so our next section, liquid penetrant inspection. This is going to be the third of those first 3 labs that you're going to be performing. So after we've done this, starting today, the group that has lab today, I'll begin demoing liquid penetrant with everybody. In fact, I will demo what's called portable liquid penetrant inspection with everybody, and then I'll kind of do half and half with each group, where I'll go through how to use our bench and whatnot. We won't probably quite get to all that today, so when we do this in lecture next week, barring any more snow days, when we do this in lecture next week, it'll probably be kind of a review for those that have the process today in lab. So starting out, our advantages and disadvantages. So liquid penetrant inspection is highly reliable. It's very good at finding fairly small, very, very small flaws, and cracks being the primary one. It can be easy to perform, and we'll talk about why that is. There's, depending on which techniques you're using, what size cracks you're trying to find, and which combination of different materials or different test materials you're using. It can be easy. Some materials are more sensitive than others, and so some of them, it can actually make it a more difficult process because they are there are certain ones where it's very, very process intensive, and slight changes in timing and things like that can make a big difference. It can be pretty inexpensive, even at the higher levels. It's still relatively inexpensive. The basic portable aerosol can setup that we'll use in lab, and that was probably the one we used out in industry more than anything else, just because a lot of times we had to do it on the airplane, so it made more sense to have portable than a fixed. You need 3 cans. You need a cleaner, a liquid penetrant, what's called a developer, and those cans are about $15 to $20 a piece. So you can have a full setup minus the black light. You can have the full setup to perform liquid penetrant inspection for under $60. The black light, different story. You can get a black light pretty cheap on like Amazon or something like that, but it's not going to be certified. Technically, you have to have a certified black light in order to perform these inspections. And just to give you an idea, the little flashlights that we have that you'll be using, which are a certified flashlight, those are about $600 to $800 a piece. And so, compared to, and then if you want anything bigger than that, the price goes up. That's about as low cost point for a certified black light as you can get. Yeah. Certified means that it is, remember when we were talking about magparticle, we looked at 3,650 nanometers or 360 angstroms being the ideal frequency of the light. It narrows it down to a very narrow band in that range. The black lights you get on Amazon have they don't control that range as much. And so the big issue, they may have more UV light, hopefully not, because you don't want a lot of UV light. That's what excites the fluorescence part of it. But the problem is they may stray into the visible light range a lot further. And so you get a lot more visible light, which contaminates your ability to see, can potentially contaminate the ability to see it. In all reality and practicality, most of the time it doesn't make a big difference. I have some just cheapy black lights that we've gotten, and I've used them, and you can see for what we do, you can see all the same stuff you can see with our expensive flashlights. But if you're in industry and you're going to be signing something off as serviceable, you have to have that light that has a traceability certificate with it that says this is the frequency of light that this gives off. And by the way, it doesn't give off more than this amount of these other frequencies of light. So that's where it comes in. That's where the cost comes in. It's highly sensitive, as I mentioned, and it can be done fairly quickly. There's some things in it that there are times where you have to let the part sit with the dye on it or with the developer, where you can't necessarily speed that up. It can be anywhere from 10 minutes to, in some cases, an hour. However, you can have multiple, you can process the actual processing time, applying like the penetrant, for instance, takes all of a matter of seconds. So you can have a lot of parts kind of all in process at once. And then as their time, as they come due, you can just start inspecting. So it can be done in a high volume environment. It's just a single part may take a period of time to get through. Disadvantages with LPI. LPI is surface flaw only. So try to get those numbers off our screen here real quick. Why is that doing that? Let me fix this real quick. There we go. That should fix it. So yeah, as I say, it is surface flaw only. Come on. Not doing that. There we go. Which means that we can't find subsurface flaws. Like we talked about with magnetic particle, there is the ability oftentimes to see some subsurface flaws. Later in the semester, when we talk about eddy current testing, more ultrasonic testing, thermographic inspection, those can detect subsurface flaws. In fact, that's what the primary use in aviation for something like ultrasound is, subsurface flaws. Cleanliness, we have to remove paint. The problem with paint is that you have to be able to get to the crack. Sometimes paint doesn't crack when the material underneath does. Creates a hard candy shell over top of it, right, which would prevent dye from getting in it. The other thing that can happen is sometimes you'll have paint that has cracks in it where the underlying part is not cracked. And so then those paint cracks absorb the dye and those show up like crack. You don't know, is it in the metal? Is it in the structure? Is it just some kind of superficial cosmetic damage that I'm picking up? And so really this process has to be done on a clean part that doesn't have any paint on it. Cleanliness is important because we're putting chemicals, penetrant, developer on our part directly. We don't want any contaminants on the part to react with those. Things like these are oil-based, which means things that are used to clean oils, things like alcohol and mineral spirits and other things like that. If those are present on the part, they can react with the dye and break down the dye and make it so it doesn't work properly. And then some of our developers are like powder form. If you have dry powder and you have a part that's damp or wet, then your dry powder is going to cake and it can cause it to not develop properly. We have to be careful about using mechanical cleaning methods. So we have to be able to remove the paint, remove all that, but we can't just go through our part into a shot blaster. Any idea why, what the problem with mechanical cleaning might be? Know what mechanical cleaning can do to very small cracks? It actually does the opposite. So it can actually peen the surface over and make them appear smaller than they are. Right? It acts like a shot peen at the microscopic level or at the grain, sand grain or walnut shell grain size. Sometimes you can use some of those softer materials, the plastic beads or the walnut shell type. But if you're using a metal bead blaster on aluminum, it's very likely going to peen that surface back closed where you wouldn't be able to pick up the flaw. So usually we have to use like a paint stripper, a chemical paint stripper, in order to remove the paint in the areas we're going to be inspecting. It does rely on visual detection. At the end of the day, you're an inspector looking at it. It can be very messy. We're dealing with dyes. The dyes get everywhere, especially when you're using aerosol dyes, they get everywhere. So be careful of things like overspray and whatnot. And then certain methods are very process dependent. That's what I was talking about. Without practice and experience, it's easy to not perform them correctly. But again, the methods we're using, the versions of liquid penetrant we're doing are very, very forgiving. Those are methods used that can detect smaller flaws and are typically used in more of a lab or a back shop environment rather than out on the floor, right, out in the hangar. So here's our general process. We're going to pre-clean our part, apply our penetrant and allow it to dwell. We have to remove excess penetrant. We only want the penetrant that is in our flaws that we're going to look for. We apply a developer, allow that to dwell or develop, depending on how you want to call it. And then we'll inspect the part. We'll look at each of these steps in detail here as we go along. But before we get to that, we got to learn a little bit more about what makes up liquid penetrant testing. So there's a few different things that you have to know when you're classifying how you are performing LPI on a part. Okay? The first is we have to know what type of process we're using, what type of penetrant we're using. And there are two types. There's type 1 and type 2. Type 1 is our fluorescent penetrant. And that's what you have to, in aviation, that is the standard for aviation. So that has to be viewed with a black light. It comes in the higher ranges of sensitivity levels. We'll talk about sensitivity levels in a minute. So it can find the smaller cracks, which is the reason we have to use it in aviation, because usually the cracks we're looking for are quite small if we're doing this. There is a range of sensitivities available. Kind of rule of thumb, the more sensitive it is at picking up cracks, the more sensitive it is to the process. And so those penetrants that can find the smallest cracks that are the most sensitive, they're also the ones where it's the easiest to screw up or that's the hardest to perform correctly. And these can be done in a portable setup or on a test bench. And we're gonna, in lab, you're gonna do each of them. You're gonna perform it with portable and on a test bench. The other common type, the other type of penetrant is visible penetrant or color contrast. Most of these are that you view with white light or visible light. And these are more industrial use, more for manufacturing, less critical manufacturing. So they're not really used in aviation. There are some GA applications where they do allow this, but if you're working on any kind of transport aircraft, they are going to specify type 2, or sorry, type 1, excuse me, type 1 fluorescent. These are almost always portable and they don't require a dark space or a black light, which is where they do have an advantage in that regard. But again, not allowed by pretty much any of your transport aircraft. So you're not going to be able to perform type 2 on a Boeing or an Airbus, on an Embraer, on a Bombardier or Mitsubishi. You know, you're going to have to use type 1 for that. I believe Cessna does allow type 2 on some of their parts. A few of the other manufacturers, but again, for the most part, this is not, you know, they're not sensitive enough because it only comes in what's called level 1. So that brings us to the next thing. So when you're doing your labs, you have to know which type you're using, and the lab will tell you, the lab sheet I give you tells you, are you doing type 1 or type 2 on a given part? The next thing you need to know is the sensitivity that you're of inspection you're performing. And so they come in 5 levels, but just to make it, you know, extra confusing, rather than calling them 1, 2, 3, 4, 5, they call them 1/2, 1, 2, 3, and 4. And this is given by a mil spec. And so, you know, level 1/2 is ultra low, level 1 low, you can see there. Most of what we're going to do in aviation and most applications, we need level 2, which is medium. Getting into those high and ultra high environments, those can be, especially level 4, ultra high, that can be very difficult to perform correctly and takes a lot of practice. What plays into, you know, the level of the penetrant is the penetrant characteristics. So a few terms that you need to be familiar with. Surface tension, this is the cohesive force between the liquid molecules, and it forms that layer on the surface, right? I'm sure you've seen like beads of water, right? Or you've seen like insects that are able to kind of stand on the surface of the water till the fish comes up and eats them. And so that's the surface tension. That's the individual water molecules want to kind of hold together. Capillary action, liquids like to rise or climb within a category or other wicking material. And so capillary action is that process, okay? Liquid flowing over a surface is known as wetting, how well it wets over a surface. And then viscosity is a fluid's resistance to flow, which you should all be familiar with in your study of oils and things like that for engines, right? So if we look at them here with our penetrants, is we want a penetrant that has good wetting characteristic. We want it to spread over a part. We don't want it to bead on the surface, right? We don't want it to be like Rain-X. We want it to actually wet the surface of the part. And then when it encounters some kind of a very small opening, like a crack or other flaw, we want that penetrant to get pulled into that. And that's where the capillary action side of things comes from. So capillary force is the surface tension here in the water or the liquid, right? Is holding this together, but it's also trying to pull up against the inner surface of this flaw. So a capillary tube's like a tiny little glass tube that's used to test this. And so that capillary action, the force that's doing is, in this case, it shows how it can overcome gravity. It's pulling this fluid up into the capillary tube because of the surface tension of the fluid. Okay? So we want a penetrant that has good capillary action, that pulls itself into those cracks, because that's how we're going to find our flaws. We're going to apply penetrant, and then we're going to look at where that penetrant gets pulled into a flaw or into a discontinuity in the part. The wetting action I talked about is trying to make sure we cover the whole surface of the part, right? We want this fluid to touch the whole surface so it gets everywhere. So we want a fluid that has a good wetting action. And sometimes the surface of the part, that's where part surface preparation comes in as well, right? That needs to, however it reacts to the fluid we're using, we want it to spread over it, cover the whole surface so that capillary action can then pull that penetrant down into the part. So if you put your dye on a part and you notice that it's creating droplets, that it's doing this, you've either got a mismatch between material and penetrant, or whatever your part is has some kind of foreign coating on the surface. You know, the one that people are most familiar with cars is your Rain-X, right? It causes the water to bead off your windshield. So you may need to clean the surface of your part better in order to get that wetting action to take place. So I'm going to go ahead and leave off there.